In this video, I will demonstrate how to create a Comsol multiphysics model with a geometry from ProEngineer synchronized through LiveLink for ProEngineer. I will model the resistive heating of a bus bar made out of copper. The bus bar conducts electrical current from bolt A to bolts B and C, and it's cooled by natural convection in the surrounding air. In the model, I will study how the temperature increase depends on the size of the design by applying a geometric parameter sweep over the width and length dimensions. To conduct current in an energy-efficient manner, I want to keep the temperature increase of the device to be less than 30 degrees above ambient. While setting up the simulation, I will go through the following steps: linking the dimensional parameters in ProEngineer to the Comsol model, initializing the simulation in the model wizard, synchronizing the geometry and parameters, defining the materials and the physics, configuring the solver, and evaluating the results. While modeling with LiveLink for ProEngineer, both Comsol Multiphysics and ProEngineer are running on the computer to allow for the geometry synchronization between the programs. The assembly, which I've already opened in ProE, consists of the bus bar and the connecting bolts. I will select the necessary parameters in ProE to control the length and width of the model from Comsol. To edit the individual parts in ProE, click Settings, Tree Filters, and check the Features box. Right-click on the base extrusion feature of the bus bar component and select the Comsol parameter selection. The dialog box contains a list of parameters for the feature and a list of parameters that will synchronize with Comsol. I add dimensions D5 and D6, which are the length and width dimensions respectively. Click OK to confirm the selection. Now I can switch to Comsol and start setting up the analysis in the model wizard. 3D is selected by default, and we'll choose Joule heating for the physics. Select a stationary analysis and click Finish. In the model builder, I start in the geometry section. For this model, add LiveLink for ProEngineer to synchronize the geometry. Click Synchronize and the geometry appears. The parameters previously selected in ProE are synchronized as well and appear in the Parameters section. In the CAD name column, I can see their names as they appear in ProE. In the Comsol name column, LiveLink automatically generates Comsol model parameters. These parameters can also be found under Global Definitions in the Parameters node. Here, I can change their values to trigger a synchronization with ProE where the geometry is regenerated and transferred back to Comsol. To synchronize, I can build the selected geometry I just changed. This new bus bar becomes a lot larger. Click the Zoom Extents button to fit it inside the graphics area. To set up the physics analysis, I need some additional parameters, which I import to the Parameters node. Use the Load from File button below the table to do this. Two parameters are added to the table. One is the heat transfer coefficient for the convective cooling boundary condition, and the other is the voltage applied to the bus bar. I can now move on to choose the materials for the bus bar and bolts. Right-click the Materials node to open the Material browser. For this model, I choose titanium for the bolts and copper for the bus bar. Now I will set up the boundary conditions. First, I find the convective cooling boundary condition. I apply it to all the outer boundaries except the three connecting surfaces of the bolts, which I'm excluding from the selection. Before moving on to the next step, I also need to enter in the heat transfer coefficient, the parameter HTC. Next, I select the ground surfaces for the current conduction problem, the faces of the two lower bolts. The last boundary condition to set up is the electric potential, which is applied to the upper bolt. I type in the parameter name for the applied voltage, VTotal. Now I will add a domain probe, which can be found under the Definitions node. I'm adding a domain probe to monitor the average temperature increase in the device. I will change the expression to give me the increase from ambient, 20 degrees Celsius. A default normal size mesh will automatically be generated, so I'm skipping the mesh section and moving on to configure the parametric sweep, which I add to the study node. The parametric sweep can sweep over any parameters defined in the parameters node under global definitions. To specify the parameters for this sweep, I click the Add button below the table. This adds the first parameter to the table, the width. Use the Range button to define the range. I'll start at 40 with a step size of 20 and stop at 80. Add the second parameter to the sweep, which is for the length of the bus bar, and define a range from 60 to 100 with a step size of 20. One more setting is left before solving, as I want the sweep to include all combinations of the specified parameter values. To compute the sweep, right-click the study node and select Compute. During the sweep, Komsol solves the model for each parameter combination and updates the results table with the evaluated temperature increase. I can also follow this process in a plot. For each new parameter combination, the values are synchronized with ProE, where the geometry is rebuilt and synchronized to Komsol. Back in Komsol, the sweep is almost done, and I can see how the temperature increase lowers for the larger dimensions of the bus bar. To get a better view of which combinations of parameters keep the temperature increase in the desired range, I create a surface plot of the table. With the length and width parameters on the two axes, I can see which combination of values give a temperature increase below 30 degrees. To get an even clearer view, I can use the slider to limit the data range to 30 degrees to show the plot only where the temperature increase is below 30 degrees. For more information, visit our website.